Hello student, I am Sudha Rani Dehri. In previous lecture, we defined complex numbers. We discussed that complex numbers are of the form a plus ib, where I was the value of square root of -1 and a and b were real numbers. We also discussed that for any positive integer a, the value of square root of -a was I times square root of a. We also calculated the powers of I and so generalized it as for an integer k, the value of I to the power 4k was 1, value of I to the power 4k plus 1 was I, value of I to the power 4k plus 2 was -1, and the value of I to the power 4k plus 3 was -I. In today's lecture, we will form some examples of complex numbers, and we will define what are real and imaginary parts of complex numbers, as well as we will calculate modulus, conjugate and multiplicative inverse of complex numbers. Now, let us see how we can form examples of complex numbers. According to the definition of complex numbers, numbers of the form a plus ib are called complex numbers, where a and b are real numbers and I is the value of square root of -1. It means that we can choose a and b any real number. In first example, I have taken a and b integers, and so I have formed first example as 2 plus I3. In the second example, I have taken a as an irrational number root 2 and b an integer 3. So, second example is root 2 plus I3. In the third example, I have taken a as a rational number 1 upon 11 and b as an irrational number root over 5, and so the third example is 1 upon 11 plus I times root over 5. And in the last example, I have taken a as an integer 4 and b a rational number 1 upon 7, and so the last example is 4 plus I times 1 upon 7. I have formed some examples of complex numbers. Now, choosing a and b any real number, you can form many examples of complex numbers. Complex numbers are denoted by z, and therefore now we can write z is equal to a plus ib, which means that complex numbers are of the form a plus ib. Now let us come on the definition of real and imaginary parts of complex number. Suppose we have z is equal to a plus ib, then real parts of z denoted by rez will be a, and imaginary part of z denoted by imz will be b. Here you can see that since a is a real number, so we are saying that a is the real part of z. But can you guess why we are calling b as imaginary part of z? You can notice that b is with I, where I is called an imaginary unit. So, I times b is called imaginary number. So, even though b is a real number, we call b as imaginary part of z. For example, if we take z is equal to 2 plus I3, then real part of z will be 2 and imaginary part of z will be 3, since 3 is with I. Now you can think, there we were given a complex number, and so we were finding its real part and its imaginary part. But what happens if we already know real part of a complex number and imaginary part of a complex number? Then can we find the complex number? For if I say we have real part of z as a, imaginary part of z as b, then can we find z? Yes, of course. In fact, z will be equal to a plus ib. Now, we can see that real part of z was a, imaginary part of z was b, where a and b were real numbers. It means that a and b can be 0 also. because 0 is also a real number. So the possibilities are either real z can be 0 or imaginary z can be 0 or both of them can be 0. So we will see the possibilities one by one. Suppose real part of z is 0. It means a is 0. So if we put the value of a in z is equal to a plus ib, we have z is equal to 0 plus ib, and which gives us ib. And as we discussed that the product of a real number with I gives imaginary number. So in case when real z is 0, z is nothing but a purely imaginary number. Now let us move on the second possibility. If imaginary of z is 0, it means b is 0. And if we put the value of b in z is equal to a plus ib, we get z is equal to a plus I0, which is nothing but a plus 0, and it gives us a. Since a was a real number, so we can say that when imaginary of z is 0, then z is nothing but a real number. Now the third possibility is that when both real of z and imaginary of z are 0. In case real of z is 0 as well as imaginary of z is 0, it means a is 0 and b is 0. And when we put the value of a and b in z, we can see that z will be nothing but 0 plus I times 0, which will gives us the result 0. It means that when we have real part as well as imaginary part 0, then the complex number itself is 0. Now let us see how can we calculate modulus of a complex number. Suppose we have z is equal to a plus ib, then modulus of z denoted by this is nothing but a non-negative square root of a square plus b square. For example, if we take z is equal to 2 plus I3, then modulus of z will be square root of 2 square plus 3 square, which will give us square root of 4 plus 9, and it will give us square root of 13. We will also see how can we calculate conjugate of complex numbers. Suppose we have z is equal to a plus ib, then for finding conjugate of z, we have to keep the number same, but we will change the sign. Since z is equal to a plus ib, and if I find conjugate of z, then conjugate of z denoted by this will be nothing but a minus ib, where a and ib has been kept as same, but we have changed the sign. For example, if we take z is equal to 2 plus I3, then conjugate of z will be 2 minus I3. Since in z we have plus sign, so in conjugate of z we are taking minus sign. In another example, if we take z is equal to 5 minus I7, then conjugate of z will be 5 plus I7. Since in z we have minus sign, so in conjugate of z we are taking plus sign. Now finally, we move on the multiplicative inverse of complex numbers. Suppose we have z is equal to a plus ib, then what will be the multiplicative inverse of z? Before proceeding ahead, I would like you to define what is actually multiplicative inverse. If we have a number z, and if I am asked to find multiplicative inverse of z, it means that I have to find a number such that it is when multiplied with z, we get result 1. And you can see that 1 by z is the number which is multiplied by z gives 1. It means that multiplicative inverse of z will be 1 upon z, and it is denoted by z to the power minus 1. Now we will see what will be actually 1 upon z if z is equal to a plus ib. Since 1 upon z, if we put the value of z, we get 1 upon a plus ib. Now I would like you to remember that while rationalizing a denominator containing irrational number, what we used to do? We used to multiply and divide the fraction with denominator's conjugate. Similarly, we will do here? We will multiply the fraction 1 upon a plus ib and divide the fraction 1 upon a plus ib with the conjugate of a plus ib. Since the conjugate of a plus ib is a minus ib, so actually we will multiply the fraction 1 upon a plus ib and divide the fraction 1 upon a plus ib with a minus ib. Now, before proceeding ahead, I would like to define how we multiply two complex numbers. Suppose we have two complex numbers a plus ib and c plus id. Then we take their multiplication as, first we multiply a with whole c plus id and then plus, and then we multiply ib with whole c plus id. Similarly, if we proceed here, we will see that a is multiplied with whole a minus ib and then plus sign, and then ib is multiplied with whole a minus ib, which will give us a square minus iab plus iab minus I square b square in the denominator, and multiplying the numerator we will get a minus ib in the numerator. When we solve the denominator, we see that in the denominator we are left only with a square minus I square b square, and numerator remains as it is. Now in next step we put the value of I square as minus 1, and when we solve all this, finally we get a minus ib in the numerator and a square plus b square in the denominator. Now you can see that when z was equal to a plus ib, then conjugate of z was a minus ib, and modulus of z was non-negative square root of a square plus b square. It means a square plus b square can be written as square root of a square plus b square, which is nothing but square of modulus of z. So we put the value of a minus ib and a square plus b square, and finally we see that multiplicative inverse of z is nothing but conjugate of z upon square of modulus of z. Now let us see an example. If we have z is equal to 2 plus I3, and if we have to find multiplicative inverse of z, then using the formula that z inverse is equal to conjugate of z upon square of modulus of z, we get 2 minus I3 in the numerator and 13 in the denominator, because when z is equal to 2 plus I3, then conjugate of z will be 2 minus I3 and modulus of z will be square root of 2 square plus 3 square, which will give us square root of 4 plus 9 and which will give us square root of 13. And when we square both the side, we see that modulus z square is nothing but 13. We can also find multiplicative inverse of 2 plus I3 by another method. In this method, we will write z inverse as 1 upon z, and we will substitute its value, and we will multiply this fraction and divide this fraction with the conjugate of the denominator. Conjugate of 2 plus I3 is 2 minus I3, so we will multiply and divide this fraction by 2 minus I3 and 2 minus I3. Now solving this, we will see that 2 minus I3 is in the numerator, and finally denominator will be 2 square minus 3 square. And solving the denominator, finally we will see that we are getting 2 minus I3 upon 13, which can further be written as 2 upon 13 minus I times 3 upon 13, and it can further be written as 2 upon 13 plus I times minus 3 upon 13. We can notice here that this is nothing but in the form of a plus ib, where a is 2 upon 13 and b is minus 3 upon 13. So we can see that any fraction can be written in a plus ib form, as I just discussed now. So today's question is, you have to express this fraction root 2 plus I times root 5 in the numerator and 1 plus I times root 3 in the denominator in a plus ib form. In today's lecture, we saw some examples of complex numbers, and we saw that complex numbers are denoted by z, and if z was equal to a plus ib, then real part of z was a and imaginary part of z was b, and if we take real part of z as 0, then z was nothing but ib, and so it was called purely imaginary number. We also discussed that if we take imaginary part of z as 0, then z was nothing but a, which was a real number, and if we take real part of z as 0 and imaginary part of z as 0, then the complex number was itself 0. We also calculated that if z is equal to a plus ib, then modulus of z is non-negative square root of a square plus b square, and conjugate of z is a minus ib, as well as multiplicative inverse of z is conjugate of z upon square of modulus of z. In next lecture, we will see how can we say that two complex numbers are equal. We will also see some algebras of complex numbers, and we will prove some identities of complex numbers. Till then, take care. Thank you.